So to look at different possible directional antennas, what we looked at right now, the first thing was to look at waveguide horns. A waveguide horn is an antenna that always works. The only problem is that to get a reasonable illumination efficiency of the aperture of this antenna, we need very long horns. We get a square phase error, and the square phase error can be handled with dielectric lenses, converging dielectric lenses, can be handled with converging mirrors, parabolic mirrors. There is yet another possibility to build higher gain antennas, and that's the solution to make arrays. So today we are talking about arrays. Out of all different possible antennas, probably arrays are the antennas you are mostly going to get involved with, because arrays, you can also build your own arrays from ready-made antennas. And that's what an engineer has to do, though he is not an antenna engineer. He just has to perform some radio links, some network, has to make the obtain the desired coverage of his radio system. And here where different antennas are combined together, connected together to get the desired coverage out of. And this is where things go wrong, usually. Things go wrong, why? Usually what you can buy is some antennas that have some directional patterns, like one horn here and another horn here, connected to the same generator. This is the generator here. So to get the desired coverage out of antennas that already have some kind of radiation pattern. So these two antennas, this one has maybe a radiation pattern in this direction. This one has a radiation pattern in this direction. What are we going to get out of this? Well, the desired outcome of this, if this was F1 of theta and phi, and this was F2 theta and phi. What is the desired outcome? Well, people usually think that this thing will simply sum together. It will obtain something like that. To have a broader coverage, say in the horizontal plane, if this table is, if this board is the horizontal plane. This usually doesn't happen at all. So this is desired. But this doesn't happen. What actually happens is that these two beams may sum into one narrow beam in this direction, or there is yet another possibility to have some zeros in between. So we have something like this. Depending all on the spacing between the two antennas, if we put here a spacing, and depending on the lengths of the lines, say L1, L2, so the phases the individual antennas are supplied with. So usually the desired thing doesn't happen. The orange diagram here, forget it. Usually other things happen. Why? Because we always have to deal with a Phasor sum. So the field both is a vector, this electric field, and is a phasor. Vectors, okay. Say we have both antennas polarized in the same direction. Have an identical polarization. But if we have the identical polarization, But we didn't care about the phase, and the phase depends on the length of the feed lines, and the phase also depends on the spacing of the two antennas. So there are things we didn't account for. We just looked at this as a scalar feed or as a very, very broad path signal like light. If we had two spotlights here, a light usually emits a broad spectrum so that we can see colors. And with a broad spectrum, all interference effects disappear. While with narrowband signals like radio signals, we see the interference effect here with as peaks, as maxima and minima in our radiation pattern, and it's certainly not desired to have some minima in between here. It's much worse than using a single antenna, putting two antennas together. Also, people that decide about these antennas are usually managers that know nothing about antennas. Usually such a disaster happens even on satellites, such a disaster, because people know nothing about antennas. So today we have to look at arrays. We have to see how to arrange antennas in simple fashion to get some useful performance, some useful radiation pattern, and maybe also to get some gain. Sometimes gain is the desired property we would like to get from antennas. How to make these things. And the first thing we are going to talk about is pattern multiplication rule. So when can we multiply patterns? What are the conditions? Say I have an array made from three antennas. First antenna, second antenna, and third antenna. These antennas have feed connections here, so feed them from the transmitter, and I may, in general, I may supply the antennas with different currents, say I1 here, I2, I3. So now when the pattern multiplication rule applies, it applies when I have first three identical antennas. That have a radiation pattern of one element, f of theta and of phi. Second, when I have same orientation. Say all three antennas here point in the same direction. Of all the elements. And the third point is that I have the same polarization. When I have the same polarization, so say if the top antenna here has vertical polarization, all the other antennas are oriented in the same way. Say both the radiation main lobe is oriented in the same way, and the polarization is the same, also oriented in the same way. Then the rule applies. And what is going to be the result out of this? The whole radiation pattern of our array, theta and of phi, is now the multiplication of f of an array of theta and of phi, array of isotropic sources fed in the same way, multiplied by the radiation pattern of an element of theta and of phi. Where I have this f of array, I have to arrange isotropic sources exactly at the same locations as I had the complete antennas. So these are isotropic sources, exactly at the same direction if I had here spacing H1 and H2. Also here I have H1 and H2. Say H1, 2, H2, 3 to use the same numbering with the antennas to H1, 2, H2, 3. So this is the pattern of the array, is the pattern of putting isotropic sources at the same locations where I had my antennas, and I can calculate this in advance regardless of my radiation pattern of a single element multiplied by the radiation pattern of a single element. Of course, these isotropic sources have to must be fed with the same current, so I1, I2, I3. And this is simple multiplication here. I wrote the dot, but it's not a scalar product. There are scalar functions, so just to indicate multiplication. So this thing holds, and we are going to use this thing, this pattern multiplication rule, to a good extent, say, to simplify our calculations. Today we are mostly going to deal with isotropic sources, point isotropic sources, just to see what is the effect of the array. Then we can multiply everything with the element array. This pattern multiplication rule does not apply here, because here I may have two identical antennas, but they are oriented in a different way. So point 2 doesn't hold, and I don't know anything about polarization of these antennas. Also point 3 doesn't hold, same polarization also doesn't hold. So this doesn't hold for this case here. But this was just an example what people can do with antenna arrays. Still, we have things people do not understand. What would people like to have? People would like to know what the directivity is of this array. As long as we know the directivity of one single element, usually when we buy an antenna, we buy our elements, we already know the directivity of the element. And unfortunately, there is no such thing as multiplication rule of the directivity. So the total directivity is not equal of the directivity of the array multiplied by the directivity of the single element. This is usually not true. So such a law about multiplication of directivities usually doesn't hold. Though people, on many occasions, people think about multiplication of directivities and think, okay, I have an antenna of 10 dBi, for instance. I make an array of 3. An array of 3 might reach a directivity of 5 dBi, and 10 dBi plus 5 dBi is 15 dBi. It doesn't hold. This thing does not hold here. So remember that there is no such rule. So there is no such rule as directivity multiplication. Only patterns get multiplied if we fulfill all these conditions. But there is no such rule about directivities. Nothing about that. So now to see what can we do with an array, it makes sense to look at the simplest possible of all arrays and try to get its radiation pattern and see what kind of patterns can we make with our array. Because in the final instance, what we are going to do, we are going to calculate the whole directivity of the whole. Here we will have, of course, the whole radiation pattern, f of theta and phi, for p. Forgot for p. Maximum, and here maximum radiation, squared, divided by the integral over the full solid angle for p here, for p. Don't have the space, and so we make the integral over the full solid angle for p of power radiation pattern f of theta and phi squared d omega. But we have to calculate the full direction pattern. Here we may apply the pattern multiplication rule. But the multiplication is applied here, and this yet has to be calculated. There is no such simple rule as directivity multiplication, though people on many occasions think about that. They put two antennas and they think that two antennas making an array with two antennas will give 3 dB more gain than one single antenna, because 3 dB is a factor of 2. That's not true. That does not hold, and we will see today why it does not hold. So let's now look at the simplest example we can think of, and the simplest example is just two elements, an array made of two elements, x, y, z. And I put these elements on the z-axis just to have geometry simple. We will also look at other possibilities, I1, I2. The distance is h, so this is h half, and this is h half, the distance between the two. And we are going to calculate the field of these two elements at a particular point in space up here. So here we are going to calculate the electric field. What is the pattern of a single element? This is an omnidirectional, so both sources are omnidirectional sources. If both sources are omnidirectional sources, I can write the field of just one source, say E1, is now polarization of the first source direction. It's proportional to the current in the first source, is delay to the jkr1, when r1 is this here, divided by r1, and there is no pattern because it's omnidirectional. And we could also write the electric field for the second antenna is polarization of the second. Same constant alpha. Constant alpha depends on how the antenna is made. I2 e to the minus jk r2 divided by r2. So really this electric field here will be really something like a vector sum here of E1 and E2. Vector sum that is smaller than a scalar sum because there is some angle in between. At an arbitrary angle theta. So this angle here is theta as usual. This is R2 and this is R from the spherical coordinates. And now, to see this thing more in detail, we have first to find expressions for R1 and R2. R1 and R2 using the cosine theorem. So the cosine theorem for the top triangle, so this point, this point, this point, the top triangle, the cosine theorem is r squared plus h half squared. So this side, the longest side, this side, minus twice r times h half times cosine of theta. R2 is very similar, but remember that here we have this angle that is pi minus theta. So if I put in pi minus theta, the cosine changes sign, so it's r squared plus h half squared, plus now twice r h half cosine theta, because cosine of pi minus theta is minus cosine theta. So that's just, I already included this different angle here. And we could put this in the fields to calculate everything. Now, what can I simplify things? I'm only interested in the far field region. So, far field. When R is larger, hopefully much larger, then our distance between antenna is 2h squared. This is the dimension of my antenna array divided by lambda. Okay? We are only interested in far field, maybe also here much larger. What can we say in the far field? In the far field, you see that these two vectors, E1 and E2, become almost parallel. So the polarization is 1p1, is approximately 1p2 in the far field, is approximately 1p, just polarization. I don't even care about polarization here. We could even have fields that have no polarization, say putting two loudspeakers and listening to the interference pattern of two loudspeakers supplied by the same audio amplifier. Also, the denominators, 1 over R1, this is just amplitude, is approximately 1 over R2, is approximately 1 over R. So in the denominator, this is just amplitude. In the denominator, it can be the same. The only thing that really matters in the far field is the phase. The phase is not arbitrary, and the phase is important in the far field, and we should find a simplification for these two expressions here in the far field. First, we could forget about this term here. H squared is very small with respect to R. We only consider this term here. So we make a simplification of the square root, simplifying the square root, just taking the largest term of the square root. And what we get here, in both cases, we get R minus plus. And this is R times H, because the 2 cancels out. R times H, if I exposed R squared before, I have R over H, multiplied by R is H. And because of the square root is H half. H half cosine theta. H half cosine theta. Okay? So now I can rewrite the whole field. The whole field is, of course, E1 plus E2 is approximately, now I approximate all the simplifications I could make. I could expose just one polarization, whatever it is, the polarization. It does not depend on the polarization. But the polarization in the far field is the same for both sources, becomes the same for both sources, just 1p. The constant alpha is the same, but also the denominator is the same for both, so 1 over R. But what is different is the two currents are different, so it's I1 times exponent of e to the minus jk R1 plus I2 e to the minus jk R2. Now I want to further simplify these things, introducing R1 and R2, our simplifications for R1 and R2, in the far field. When this holds, I can readily use these simplifications. The simplifications, what happens out? Again, simplifying 1p for polarization, alpha over R. Then I have this, I will write this simplification separately. So e to the minus jk R1 is equal to what? Is equal to e to the minus jk R is approximately equal, taking this simplification, e to the minus jkr times multiplied by e to the jk h half cosine of theta. And the same I can do for e to the minus jkr2. So I can expose here e to the minus jkr, both have the same term. So this is delay, average delay, but the particular delay is hidden here. I1 times e to the jkh half cosine theta plus I2 e to the minus jk, because I have plus here, so it remains minus the sign. Jkh half cosine theta. And that's it. So this is the maximum simplification I can get, perhaps, for this arbitrary case of two arbitrary currents feeding two identical omnidirectional sources. And that's it. I cannot do anything more complicated today. What I can further think of here in this case, I can further think that I want to see some effect out of this array. If the array has no effect, then it's not worth building it. Each antenna costs money. So if I put two antennas, I want to have the maximum array effect. And the maximum effect will be when both currents are the same magnitude. So maximum array effect, I will have it when I1, the magnitude of I1 is equal to I2. Okay? That will give me the maximum effect of the array. How to obtain this? Simply by saying that I1 is, say, identical to I2 times an arbitrary phase shift, J phi. Or in other words, I can write I1 as I0 times e to the j phi half, and I2 as some constant I0 times e to the minus j phi half. In this way, I can further simplify my expression. My expression now will look like this. Electrical field of the array. Now, of this array that has some effect. I'm not taking any case that does not have effect. For instance, having one current 10 times smaller than the other current makes no sense. That array would have a minimal effect on the radiation pattern. When they're both of identical magnitude, then I have some effect. Okay, is polarization. Is alpha times I0. I0 takes place in both currents. Put it out. Is e to the minus jkr over r. As I got before. And what I'm left in here I'm left with e to the j phi half times e to the j k h half cosine theta plus, on the other side, e to the minus j phi half e to the minus j k h half cosine theta. Okay. So this is the maximum simplification we can do. So I see that here I have two exponent functions of the argument of opposite sign. The sum of these two is a cosine. So the sum of these two, if I have two exponent functions like e to the jx plus e to the minus jx, this is twice cosine of x. Okay? just to simplify things. So I rewrite the electric field of this interesting case. This is an interesting case where I have a maximum effect of my array. It has some polarization. It is twice alpha I0. Okay, I have two elements, I have twice the field. That makes sense. I have the delay here over R, minus jkr over R. Minus sign is not very well visible. I'm not writing nice today. And here I have cosine of what? Cosine of phi half. This is the phase shift between the two array elements, plus kh kh half. Kh half cosine of theta. And now, this term here is my actual radiation pattern. This is what I got. This is the radiation pattern of my array of theta and of phi. This is what I was looking for. For the maximum effect, I have to have identical magnitude currents, and this is the radiation pattern I get out of it. So this is our derivation. What are we going now to do with this derivation? First, we have to look at different arrays, what we want from the array. If we want the array to radiate sidewise, say in the x or y direction, so in the xy plane, this is called a broadside array. This has a maximum, so theta maximum is now equal to p half. P half, theta maximum p half, this is the xy plane. On the other hand, I may have an Endfire array. An Endfire array that has the maximum radiation in the z-axis, so theta maximum may be equal to 0, or the other possibilities may be equal to pi. May radiate or in the plus z direction or in the minus z direction. May also radiate in both, but in the axis. So the Endfire array radiates in the axis where the elements are located. So this is the axis z. The broadside array radiates radiates in the plane perpendicular to the location, the direction of the array. So for the broadside array, I can make a very simple intuition here. When am I going to get this thing maximum? At theta maximum is pi half. At pi half, this cosine is equal to 0. If the cosine of the whole argument is equal to 0, I get the maximum because cosine is maximum at 0. So this simply implies that the phase shift between the two elements is equal to 0. Broadside arrays are usually fed in phase. Both currents have the same phase. On the other hand, I have many more possibilities for the Endfire arrays. For Endfire arrays, I should get this argument 0. One possibility is I get this argument 0 in the plus z direction or minus z direction. In the plus z direction, cosine theta is plus 1, and in the minus z direction is minus 1. So here, what I have, this is just one possibility. I can have phi minus plus kh. But this is just one possibility. There are other possibilities to make Endfire arrays, so it's not as trivial as broadside arrays. So what are we going to do with broadside arrays? Let's see what can we obtain out of arrays. Let's try to draw some radiation patterns and see what is going on with broadside arrays. because we first have to understand simple things, and then we're going, the last hour, we're going to see more complicated arrays. But an array of 2 elements, understanding what happens with 2 elements is basic for building arrays. So for a broadside array, if phi is 0, my radiation pattern of a broadside array is now f of theta and of phi is equal to cosine of phi is 0, so phase difference is 0, kh half cosine of theta. Or in other words, k, the wave number k is simply equal to 2p over lambda. I'm not writing nice and you cannot read this thing. So k is, the wave number is equal to 2p over lambda. If I plug this 2p in this equation, so the radiation pattern becomes f of theta and of phi is now cosine of p, the 2 cancels out, h over lambda, not 2, h over lambda, cosine theta. Let's see now some examples what happens here. What happens with, say, starting with small spacing and increasing the spacing. Let's start with first example. H is equal to lambda quarter. So my radiation pattern f of theta and of phi is now equal to cosine of pi divided by 4, because h is lambda divided by 4, cosine of theta. If I plot this now, with theta going from pi half pi, f starting with 1. It's a broadside array, so the maximum will be at f is equal to 1. When I get with theta, cosine theta is here equal to 0. Cosine theta is equal to, cosine theta is equal to 0 at pi over half. So here I have this point. This is broadside array, has a maximum radiation here. But here is cosine plus 1, here is cosine minus 1. So p quarter, cosine of p quarter plus minus p quarter is 0.7. 0.7. So the actual radiation pattern looks like this. The actual radiation pattern is nothing particularly interesting here. What happens? There is yet another issue here, and it's not really this curve. It's slightly bent because I further have this cosine function in here. It's something like this. Be more accurate, just to be more accurate. 0.7 here, 0.7. Now trying to redraw this in a polar diagram. A polar diagram when I have a z-axis up here, when I have an x or y axis here. When I draw here a circle, a unit circle, here. 1 minus 1, here is also minus 1. See, here is minus 1 on x and plus 1. What is our radiation pattern looks like? Our radiation pattern has just slightly modified in the bottom. Just slightly modified. So here reaches 0.7 or minus 3 dB. So here is 0.7. And here it was 1. So very, very little effect because the antennas of this broadside array are very close spaced together. Next example, we go with our spacing. H is lambda half. So my radiation pattern f of theta and not phi is now cosine of p half cosine of theta. If I draw it here I have theta p half 0. Here I have 1. Okay, I again have the maximum up here. The maximum is 1 up here. But when I go with theta to 0 or to p, this becomes plus or minus 1. Cosine of plus or minus 1, cosine of plus or minus 1 is 0. So I get something like this. Or in a polar diagram, I'm not going to redraw all figures here. The polar diagram, if I draw the unit circle, sorry, this is wrong. Sorry, this is wrong. Now, I was already thinking at next hour the radiation pattern of Endfire arrays. Sorry, this is wrong. This is really wrong here. This is really wrong. This is really wrong here. This is really wrong. I was thinking about already next hour about the radiation pattern of next hour. So this radiation pattern here looks like this. So z, x or y, and unit circle. I'm a little bit short of time and I was running so fast that I already skipped to the next hour what I was going to tell next hour. So here I have the maximum in the xy plane. The maximum here is 0.7. 0.7, and this is my radiation pattern here. Barely visible that is not 1 like here. Very little effect because of the lambda 4. Sorry for that mistake. Here, what I have here, I have 0 radiation in the z-axis. So the radiation pattern is something like this. Yes, there is some effect of the broadside array here. Next, what we are going to see next is 3. Say the spacing of 3 lambda quarter. So the next spacing, now the radiation pattern here. I will take it absolute value because it may turn out negative, but we are only interested in absolute values while calculating the directivity. So absolute value is now absolute value of cosine of 3p quarter cosine theta. Okay, absolute value. So what happens here now? The radiation pattern just taking the absolute value. So 0 p half p theta. Okay, we always reach 1 in the broadside direction. 1. But this pattern now will go to 0 and we will have some more pattern here. To 0, and here we will jump up to 0.7. 0.7, so here and here we get to 0.7. 0.7 here. Now how the radiation pattern looks like in the polar representation. The polar representation looks like this. Z, X, and Y. Drawing the unit circle, I'm not very good drawing early in the morning, so unit circle just for comparison. I have one major lobe here. I always have the main lobe in the xy plane because it's an Endfire array. It's just slightly narrower than this one here, and I have a secondary lobe here. I also have side lobes. I manage now side lobes that get to 0.7 here, or minus 3 dB. The next thing to see, of course, is the next example is for h is equal to lambda. So the absolute value of the radiation pattern, we are only interested in the absolute value. Here is absolute value of cosine of pi times cosine of theta. What do we get here? Again, we have the maximum that pi have. Okay, it's a broadside array. We have in the broadside direction perpendicular to the axis of the array. We have to have the maximum, and here we get this. And we have side lobes here. Side lobes that have the same, exactly the same size as the main lobe. They all get up to 1 in the absolute value. So if I redraw the diagram here, x or y, here is z, unit circle. Unit circle. So what I get here identical lobes. And these lobes are quite narrow, still in the xy plane. They are still the maximum, but I have other maxima here, and this lobe is a little bit broader thanks to the cosine function in here. What could we further do? We could further look, just to finish this subject here, with one final example. If we take the example number 5, if we take h is equal to 2 lambda, then my radiation pattern, f of theta and phi, is now absolute value because it changes sign in the zeros. When you have zeros in the pattern, sign always changes. Cosine of 2 pi cosine of theta. If I sketch this quickly, p half p theta 0. So here I now have many lobes already. I have one lobe in the xy plane, but I have another side lobe here that's broader, and I have yet another side lobe here, and the same on the other side. And this all get up to 1. So what I do obtain here, if this is x or y, this is z, and I have a quite narrow lobe, but this is lobe. This lobe is actually toroidal. It's all the way around the z-axis. Here. Oh, sorry. This is not nice. I have to redraw it. Was too quick to draw things. Have one lobe here. It's becomes quite narrow. Then I have other toroidal lobes slightly broader here, and also here. And finally, I have the lobe in the Endfire direction here and here. Now, what can we say about these lobes? If we want directivity, a directional antenna, we certainly don't want this. We don't know many lobes. And here, in fact, these many lobes that we get in other direction eat lots of power of my transmitter. So this is certainly not a good solution. I don't want this. And here I have almost no effect of my array. What I really want is to have the maximum in the xy plane and some controlled side lobes. Not too large and not too small, because if they vanish, if they are too small, these lobes become wider, broader, and I lose power in the unwanted direction up here and up here. Here I can slightly squeeze these lobes on the account of these two side lobes. So the optimum will be probably in between here. We shall see next hour how to get to this output. Sorry, I'm late.